So now with an overview of the electron transport chain in mind and kind of a general roadmap and sense of what we're going to try to accomplish here, we will move on to filling in some of the finer details of the energetics of redox reactions. I think we're mostly very comfortable with redox reactions in general. We've certainly seen plenty of them. The idea of what's reduced, what's oxidized, that electrons are changing hands. But I want to convince you that we will indeed see energy release in this electron transport chain. I want to prove to you that we can release small packets of energy as we do redox reactions. So we'll start with those general principles here in this chunk. Once we get all of those energetics squared away, we'll be ready to dive into the details of the electron transport chain itself, and we'll do that in the final chunk for this Lecture 15 series. So if we're going to talk about the energetics of redox reactions, we need to talk about reduction potentials, specifically reduction potentials in the ETC, in the electron transport chain itself. There is, not surprisingly, a change in energy with redox reactions. Redox reactions are like any old reactions. Energy is either absorbed or released by redox reactions. If it's absorbed, that's an endergonic redox reaction, and if it's released, it's exergonic. So no surprise there. Let's actually consider two electron carriers, our old friend NAD+, and a newcomer that will become an old friend as well, coenzyme Q. Two electron carriers like FAD, NAD, some of the others we've discussed. Things that can be reduced and things that can be oxidized. So since these are electron carriers, they can indeed exist in oxidized or reduced forms. And the question becomes, well, which way would electrons prefer to move? Would they like to move from reduced NAD to oxidized CoQ? Or would they instead move from reduced CoQ to oxidized NAD? Which way would electrons normally move? Question is, we don't really know yet, do we? We have to first decide which ones of those directions is more energetically favorable. In other words, is energy released when electrons move from NAD to CoQ? Or is energy released as those electrons move from CoQ to NAD? Whichever one of these redox reactions has the negative delta G is the one that will be preferred. So the direction of movement, or the preferred direction of movement by electrons, is measured by using reduction potentials for each of the carriers involved. And reduction potentials are kind of synonymous with pKa's that we've discussed in the past in this course, in the sense that these are properties of the electron carriers. They can't change. It's like the electron carrier's eye color. NAD has a reduction potential, and that will always be NAD's reduction potential. So as a rule, if you're someone who likes to just memorize a simple rule and run with it all the time, here's the rule you should memorize. A molecule with a high value reduction potential will be reduced. In other words, electrons will move towards it if it is paired with a molecule having a lower reduction potential. And that molecule would therefore be oxidized, have electrons move away from it. How reduction potentials are calculated experimentally, how you can actually determine the reduction potential of an electron carrier, is covered quite well in the textbook. But we don't really go into that here. If you're curious, you're more than welcome to explore that, but I'll never assess you on that understanding. We won't be covering that material here or in any exam. Just know that once these values are calculated, they are known. They're permanently known because, again, those values never change. They're constants for each electron carrier. They're permanent. So let's take a look. Here is a table of reduction potentials from your textbook. This is table 20.1 from the textbook. And you can see right here, it's reduction potentials. And we see listed on the left lots and lots of different electron carriers, some of which are familiar to us, like FAD being reduced to FADH2, NAD being reduced to NADH2. Here's our new friend, CoQ, being reduced to CoQH2, and even oxygen is up here being reduced to water. So these are just things that can carry electrons. Just for giggles, what was the pH of the reaction when these experimental reduction potentials were determined? Do you have any idea? Look closely. pH was 7. Because look, these reduction potential values are E0 prime. We have adopted the biochemist's standard state here. But anyway, I digress. In general, Reactions near the top will occur if they're paired with oxidations lower down. Look at these reactions carefully, though. This is a table of reduction potentials showing reduction half reactions. Everything on this table is a reduction. So if we're talking about something else being oxidized, we actually have to flip the equation. In other words, malate can be oxidized to oxaloacetate because oxaloacetate can be reduced to malate. So keep that in mind always when you're looking at these tables. These are reductions and only reductions. If we're doing redox reactions and one thing is reduced, the other needs to be oxidized, and so that means we have to flip the other reaction from right to left. Also, if we have these values listed here, if we're flipping these reactions in order to create oxidations, we have to flip the value as well. In other words, we have to change its sign. So these reduction values have their signs switched if we're considering the oxidation form. It's getting a little wordy. I understand that and I can appreciate it. So let's move ahead with an example. Let's consider the oxidation of NADH. Here we have the reduction potential for the reduction of NAD to NADH, and that has a value of negative 0.32. If we consider the oxidation of NADH plus H to NAD plus, what value would that have? If we start with NADH plus H and we go to NAD plus, that would have a value of positive 0.32. We flip the reaction, we flip the sign. The reduction has a negative value, the opposite oxidation has that same value as a positive. Let's go a little further. Let's consider the oxidation of NADH coupled to the reduction of oxygen to water. Here is the reduction of oxygen to water. If we're considering these reactions as coupled, we combine their reduction potentials. So if we're saying, all right, let's keep oxygen being reduced, so we keep this sign the same. And let's combine it with NAD being oxidized, so we flip this value to its positive form. We're essentially saying the oxidation of NAD coupled to the reduction of oxygen has a total value of 1.136. Great. What do we do with that? Well, for redox reactions, we can follow the formula that the delta G equals negative the number of moles we're working with times Faraday's constant times delta E. Again, N is the number of moles of electrons we've transferred. F is Faraday's constant, which all of us know is 96.485 kilojoules per volt mole, times delta E. Delta E is the value we just calculated. This is delta E. Now let's think about that mathematically. I'm not going to ask you to calculate any delta G's here, but we're going to use this formula to teach us something very important right now. If delta E is positive, as it just was in the example I gave you, the reduction of oxygen coupled to the oxidation of NAD, if delta E is a positive value, we've got a negative times positive N times positive F times positive delta E. What sign does that give us on delta G? It gives us a negative sign. And so I'm going to give you a little jingle, a little logo, an expression, a motto to remember. Positive delta E's give us negative delta G's. We can do it the other way too. If delta E is negative, then we have a negative times a positive times a positive times a negative. Negatives times negatives are positives. So negative delta E's give us positive delta G's. Anytime we can calculate a positive delta E, we've got ourselves a favorable reaction, a reaction that is exergonic. Conversely, anytime we calculate a negative delta E, we have a positive delta G, an unfavorable reaction. Let's look at another one. The full reduction of CoQ coupled to the oxidation of cytochrome A. First, let's find those on the table. Here they are, CoQ and cytochrome A. In this example, we're saying that CoQ is reduced, so we leave this value alone, positive 0.06. And we're coupling it to the oxidation of cytochrome A. That means we have to flip the value of this one because we're considering its oxidation. Essentially what we're combining is a positive 0.06 and a negative 0.29. That gives us an overall delta E of negative 0.23. Negative delta E's give us, say it out loud, positive delta G's. And reactions with positive delta G's are not spontaneous and not going to happen. This is not going to happen. This reaction is unfavorable. I started off with a thought experiment. I started off by saying to you, well, when we consider electron carriers, we can have electrons move from one carrier to another. And I posed the question, if electrons were moving from NAD to CoQ, which way would they rather move? From NADH to CoQ, or from CoQH2 to NAD? We said at that point, we don't know. How would you know? Now, we can figure it out. I'm not going to go to the blackboard because I'm not really teaching in front of you. So I'm going to ask you to pause the lecture at this point and see if you can figure out, see if you can determine which way these electrons are going to go. And then unpause the lecture and I'll follow up with working through this problem myself and we'll see if we came to the right answer. So now that you've done your work and you have your answer in front of you, you're going to have to bear with me as I work through this myself. And I'm literally here at my office desk with a blank piece of paper and I will describe everything I'm doing. If I'm talking about movement of electrons from NADH to CoQ, then what I'm actually saying is that NADH is going to be oxidized and CoQ is going to be reduced. I'm going to come to my table and find NAD. The value of the NAD reduction is negative 0.32. But in my example here, NAD is actually being oxidized. So I'm going to flip that value to positive 0.32. If it's CoQ that is receiving the electrons, it's CoQ that's being reduced. That reduction is shown here. It is 0.06. And I'm going to leave that sign alone because in my example, it's CoQ that's being reduced, and these are reduction values. Combining those together, I get a value of positive 0.38, and that is my delta E. And then I just remember my jingle. Positive delta E's give me negative delta G's. It looks to me like this is the favorable reaction. But I want to be sure. In the second example, it's CoQH2 that is being oxidized. NAD is receiving the electrons, and so it has been reduced. Coming back to my table, CoQ being, here it is, CoQ being reduced has a value of 0.06, but here in this example, I have it being oxidized. So I'm going to have a negative 0.06 value. In my example, NAD is reduced. NAD is indeed reduced here, so I'm going to leave this alone and keep it as a negative 0.32. When I combine or add a negative 0.06 to a negative 0.32, I get negative 0.38. That is my delta E. My song tells me that negative delta E's give me positive delta G's. This is an Endergonic reaction. It requires energy, and it is therefore unfavorable. Electrons are never going to move from CoQ to NAD. That requires too much energy. Electrons will always prefer to move from NAD to CoQ because that movement is the only one that releases energy. This is why electrons flow through the electron transport chain. I told you in the last chunk that with each passage of electrons, with each changing hands of electrons, a little bit of energy is going to be released as a negative delta G. This is why, and this is how. Electrons move from carrier to achieve those negative delta G's, making the universe happy and releasing the energy that we need in order to pump protons. Now it's your turn. Without my help at all, NAD and FMN are involved in a redox reaction together. Tell me who is reduced by the end of that reaction, who received electrons. This is very much like the kind of question you might see on the next exam, so I encourage you to work through it by pausing the lecture. If you did this question properly, you should have seen that you only get a positive delta E, a positive delta E of the value of positive 0.101, only when those electrons move from NAD to FMN. It is FMN that will be reduced, receiving electrons from NAD in this reaction. That's the only one that will give us a negative delta G. If you're not comfortable with this material, certainly point it out in your reflections. It's critically important that we understand these fundamentals of reduction potentials as we work through this material. And so, taking this together, zooming out a little bit, this is the way it all works. A series of redox reactions are done in a precise succession, each one of them with a very small positive delta E, which gives us a very reasonable negative delta G. Those little bits of releasing the energy of the electrons a little bit at a time, and that energy is indeed coming from the electrons themselves, allows there to be no metabolic explosion, allows the controlled release of energy packets. And so we slowly start with high energy, volatile electrons on NAD, and we pass them slowly from carrier to carrier, releasing a little bit of energy at a time, if you look at these negative delta Gs, until eventually those low energy, low power electrons are used to reduce oxygen to H2O. This is why the electron transport chain is a chain. The order of the redox reactions matter. It's to achieve these specific and reasonable negative delta Gs that will not kill the cell. And again, to bring it full circle, it's these negative delta Gs, these packets of released energy, that will be used to pump protons against their concentration gradient, and then that gradient of stored potential energy used in turn to make ATP. So let's do it now. Let's play a game of hot potato and pass some electrons. And that's where we'll be moving as we head into the next lecture chunk.